This talk is about doing anomaly detection in P4 switches using very basic statistical primitives. Sam did all the work. It was Stefano's idea, and for some reason I'm giving the talk. So the problem we're trying to solve is we've got a whole bunch of traffic flowing through a P4 switch. And what we want to be able to do is detect when something strange happens to that traffic. Now, the conventional way to do this with a P4 switch is for your controller to instantiate some code in the P4 pipeline, maybe a sketch or something like that. And every now and then it will poll the pipeline, read out the data, and figure out what's going on, get the data back, and see if something strange happened. Now, the problem with this is that you can't really have the controller talking to the P4 pipeline on very, very fine timescales. And if you've got an awful lot of switches, then it's difficult to make this scale well. So what's the alternative? So what we'd like to do instead is to have code running in the P4 pipeline, and it's analyzing the traffic that's coming in, and maybe it's looking for some kind of a blip in some parameter in the traffic. When it sees that, it exceeds some dynamically computed threshold and directly raises the alert with the controller. But to do that, we've got to be able to do basic statistical analysis in P4. And that's the problem we're trying to solve here. So why is this not a trivial problem? Well, the problem is due to the nature of a P4 pipeline. Obviously, P4 pipelines are designed for forwarding packets. And in order to keep up with the line rate of the switch, a packet must be able to go through a P4 pipeline in a constant amount of time. And therefore, we only have a constant amount of processing that we can apply to the packet as it goes through. And this ends up applying some limitations. In particular, the first limitation we have is no loops. So we can't do any kind of while loops or for loops or anything else when we're doing any computation. The second limitation we have is no division. And most of the basic statistical primitives involve doing division. So we're going to need to be able to do our statistical analysis in a constant number of operations per packet, where those operations are relatively simple. We can't use any loops, and we can't use any division. So we're busy forwarding packets, and we're monitoring n values of interest. So these are going to form a distribution x with values x1 all the way up to xn. It doesn't particularly matter for our point of view right now what these x's are. They might, for example, be the data rates of traffic in the last n time periods, or we might be monitoring some field from the packets that has n values, and we're just counting how many of each of those values we've seen. So what are we going to do with these? We need to calculate some statistical analysis of it to be able to do our anomaly detection. The first thing we might want to be able to do is to calculate the mean. It doesn't get much more simple than that. All we need to do is sum up all the values of x and divide by n. Unfortunately, we can't iterate and we can't divide, so we're going to have to do something different. So the first thing we can do is observe that when we're doing anomaly detection, what we're going to do is pretty much always be comparing some change against the mean, and we don't really need to divide by n. We can just do a comparison of n times both of those values. So we can kind of cheat. And actually, instead of maintaining the mean, we just maintain n times the mean, and that's fine for the sort of anomaly detection we're doing. The second thing is the iteration here. Now, what happens, of course, is that each of these values changes as packets go through. And so what we're going to do is to spread the cost of calculating this iteration over all of the packet arrivals that comprise the distribution. So what happens? Well, either the particular value of xi for one of these xi's goes up by 1, in which case this goes up by 1, or alternatively we gained a new value in our distribution, in which case this goes up by that particular value of xi, and we can again modify n times the mean. So all that happens is for each of those individual packets arriving, we're either going to add 1 to this, or we're going to add the new value of xi to this, and we can do that. So what we're really doing here is spreading out the computational cost of calculating any of these into fixed time operations that are performed on each individual packet as it comes past. Okay, so we can calculate mean. Now, what about variance? Sigma x squared is defined as the expectation of the square minus the expectation squared. Now, as before, we probably want to work with n times the variance if we're going to work with n times the mean. So what we're interested in really is sigma of nx, and that's expectation of nx all squared times expectation of nx squared. Now, we've already just calculated this. This is the mean. So what we need to do is to calculate this. So what's that equal to? So that's the sum of nxi squared over n, which is quite convenient to calculate. Sum from I equals 1 to n of xi squared. So that's it. Now, how do we calculate this on a packet by packet basis? So let's give this a name. We're going to call that x sum squared. X sum square, like that. Now, how do we update the mean and the variance when packets arrive and cause our different metrics to change? Well, there's two different ways that can happen. So a new packet arrives. First thing that can happen is that actually creates a new xi in our distribution. And when we get a new xi in our distribution, we need to increase n, and we need to increase the mean by that new value that's in our distribution, xk, and we need to increase x sum squared by xk squared. Now, the other option is that we cause one of our counts in our distribution to increase. Okay, so what are we going to do here? Well, what we need to do is the mean will just increase by 1. That's easy. And x sum squared now needs to be modified. And so what we're going to do is to add to that the new value of xi. So that's the previous value plus 1 squared, and then take away the old value. And if we multiply out the brackets, that's the same as adding 2x minus 1, which again is very easy to do in quick per packet operations. So if it's a new value in the distribution or it's an incremental value in the distribution, we can quickly calculate the new values of the mean, new values of x sum squared, and so we can calculate the new value of the variance. There are quite a few algorithms where we can spread this computational cost over many packets. In the paper, we show how you can approximate the square root if you need to calculate the standard deviation instead of the variance. We can also calculate the median or percentiles. Now, suppose this is our distribution and we want to be able to calculate the median of the distribution. How do we do that? We obviously can't sort because we can't do any iteration, but we can maintain a running concept of what the median is. Suppose the median is currently here, xm, and in order to update this as packets arrive, we can keep two other counters. Low sum is the sum of all these values, and high sum is the sum of all these values. So what happens when a new packet arrives? Well, let's say it updates this particular value here. Now, what we need to do is we need to compare to see whether we need to move the median. And what we can do is we can look at low sum and we can look at high sum plus xm, and if this is bigger than that, then we do need to move the median, otherwise we don't. So if we need to move the median, how do we do it? Well, we just move the median one place to the right, and we also need to increment this and decrement this. So this is plus equals xm, and this is minus equals xm, and we're done. And this approximates the median exactly if there were no gaps in the distribution. Otherwise, because the median can only move one slot at a time, it'll only be an approximation of the median. In the paper, we show how you can use these statistical primitives to investigate a volumetric anomaly, where you monitor all the traffic on a prefix, and then when you discover something strange happening, you start to monitor all the individual /8 prefixes and progressively zoom in until you can identify which individual IP address is causing the problem. Although we've only looked at fairly basic statistical primitives, we've found the surprising amount you can achieve by spreading the computation across all the packet arrivals. I think this is a ripe area for future research.